The basic idea of a limit is that we want to determine how a function behaves at a certain point by just looking at the surroundings and not the point itself. So let's say, for example, that I would like to know how this function behaves as x approaches c. If we approach from the left, we can see that as x gets closer to c, the function gets closer and closer to some value here on the y-axis. And if we do the same thing, but this time from right instead, we can see that as x approaches c, the function seems to approach the same value as before. This value, which the function seems to approach as the x value approaches c, is called the limit. And the way we would denote this is by writing a lim, which is short for limit, of f of x as x approaches c is equal to L. So just to summarize, we started by approaching value c from right. This is called taking the right side limit, which is denoted pretty much the same as above, but with x approaching c plus instead. The next step was by going from left. This is called taking the left side limit, is right? And it is denoted pretty much the same again, but this time with x approaching c minus. And it's really important to know that this is only if these two side limits are the same that the limit exists. And if the limit exists, it's always going to be equal to the side limits values. And this is not the formal definition, by the way, but it will get you really far. So let's continue by looking at some examples, so you can test your new knowledge. So please, pause the video and try to determine what the limit is as x approaches 3 for these two cases. Let's start by determining the left and right limits. As we approach the number 3 from right, the function seems to go to the function value 2, which means that the right side limit is going to be 2. And if we approach it from left, it seems like the function value tends to go towards number 2 again, which means that the left side limit is also going to be equal to 2. So, since both the left and right side limits are the same, the limit exists, and is going to be equal to the number 2. The same procedure can be applied in the second problem. When we approach the number 3 from right, we can see that the function is always going to be on the number 4, which means that the right side limit is going to be equal to 4. While if you go from the left side instead, we can see that as we get closer and closer to the number 3, the function gets closer and closer to the number 2, which means that the left side limit is going to be 2. So, since the left and right side limits were different, the limit doesn't exist. Let's continue with the definition of a continuous function. A continuous function must fulfill that limit of f of x as x approaches c is equal to f of c for all c values in the domain. You can also determine if a function is continuous or not by looking at the graph. If you are able to draw a function without lifting your pen, the function is continuous. But if you cannot draw the function without lifting a pen, the function is called discontinuous. And a typical discontinuous function could look something like this. Note that it is this jump here that makes the function impossible to draw without lifting a pen. But what is so important about continuous functions? The answer is that they are easy to handle, as they don't just go and jump off to infinity and so on. And in this case, they will also make your limit calculations so much easier. Because if we want to determine the limit for a continuous function as x approaches some value c, then it is enough to just evaluate the function at c. But continuous functions are great for so much more than just limit calculations. But for now, I would like to show you how you can make a discontinuous function continuous with the help of limits. Let me start by writing up a discontinuous function. And those of you that say that this function is continuous, try inserting x is equal to 2. I can actually do it for you. Let's see, f of x is equal to... Okay, yeah, that did not work so well. You can never divide by 0, it's undefined. So the function is therefore discontinuous. But let us try to simplify a function. But just remember that x can never be equal to 2. So by expanding the numerator into its fractions. By doing this, we can see that the numerator and the numerator share the common factor x minus 2, which therefore can be removed. This simplifies the whole function to x plus 2. And if we graph this simplified version of the function, we can see that it's just a straight line. But we have to remember that x can never be equal to 2, as this was our condition to be able to simplify the function from the start. So this is an undefined point, which, as we can see in the graph, makes the function discontinuous. But it is also important to notice that this is the only undefined point. So if you can determine a new function value for this point, so that the function fulfills the definition, we can make the function continuous. So by looking at the definition, we can see that this new function value at x is equal to 2 should be the limit when x approaches 2. So let's see, what's the limit? If it goes from right, we can see that the function seems to approach the number 4. And if we go from the left, we can see that the function seems to approach the number 4 again. So the limit is going to be 4, which means that our new function value at x is equal to 2 should be the number 4, since this is the only way for a function to fulfill the definition. So by deciding that our new function value at x is equal to is 4, we have succeeded in making our discontinuous function continuous.